Chapter 11. So, Chapter 11 is regular polygons, and I think this stuff is really fun. I mean, one of the most fun parts because you're taking all the knowledge you've learned throughout this whole geometry course and you're using general intuition and applying it here. So, this is going to be more circles and regular polygons, right? But before we start with that, I want to talk about four vocab terms, right? The incircle, circumcircle, radius, and apothem of a regular polygon, right? So if all regular polygons will have these four things, let me draw here just a hexagon. And if we assume this is regular, I know it's not. It's actually terribly off. Let me try to fix that side a little bit, right? And if it's regular, that means all these angles are the same length, right? Or the same length, same angle measure. So it's equiangular, and all the sides are the same length, so it's equilateral. And it will always have an incircle. An incircle. And if you remember back from chapter 5, I believe, the incircle is a circle inside. Actually, let me adjust that a little bit. The largest possible circle in a shape. And that will be this here, your incircle, right? That's actually, let me get a different color for that. So it's easier to differentiate when reading. That's even worse. That's like a parallelogram form of a hexagon. Well, if I underline this in red, and then this would be the incircle, largest possible circle inside, like that. Then we have the circumcircle. The circumcircle, again, if you remember from chapter 5, is the smallest possible circle. Not the smallest. Let's see. A circle outside of a shape that contacts all of the vertices. And this circumcircle and incircle are going to be things you can only have on, the regular polygons. And then this would be the example for circumcircle, where it just touches all of these vertices and continues on like that. Next, the radius. The radius, let me check to make sure you can still see that. Yeah, I might have to bring the bottom up a bit. The radius is a line drawn from the center of a shape to one of the vertices. To one of the vertices. And that would look, if our center of this hexagon is like here, this would be like this would be a radius of the hexagon. And then let me bring this is also, you have to put in here, it is the radius of the circumcircle it's the radius of the circumcircle. And let me see if I can write apothem up here. The apothem, and this one will be important. The apothem is a line drawn from the center of a shape perpendicularly to a side, and it is the radius of the incircle. And I don't have enough room, but it is also it also bisects this in half. It bisects the side. Let's see if I can write that without smudging the ink. Bisects the side. Like that. And this would be, oh, my green was on the floor for some reason. This would be like this. Here, and it's going to be perpendicular and bisect like that. And I also forgot to add for the radius, it will bisect this angle like that. Let me add 2. It bisects the angle. And these are the 4 vocabulary terms that you'll see in this chapter. And with that, let's go on to talking about the apothem and finding area with it. See, I have to go on there. Okay. And if you're taking notes, it goes without saying I'd write all that stuff down. However it would help you. Okay, well, so first, for any shape, right? Like a square, if you have a square, this is just base times height, right? If you have a parallelogram, this is just base times height. If you have a triangle, this is just 1/2 base times height. If you have, I don't know, a trapezoid, this is height times base 1 plus base 2 over 2, right? Yeah. So we have formulas for all of these. I mean, circle is pi r squared, well, no. Oh yeah, pi r squared, like that. So this is, I mean, we have formulas memorized for this. But could you tell me what the formula is for this shape? Like a regular, a regular pentagon, a regular hexagon, whatever, what have you. Can you tell me anything above a square? Right? So we don't have formulas for all of these regular shapes. So what we use instead is a specialized formula that works for all regular polygons. It works for all regular polygons, but we just have specialized ones that work better and faster for those ones there, because we use those more than we have to find the area of an octagon, for example. Right. So this formula is the apothem. Actually, let me get a marker that writes wider than that does. I'll use this red right here. It's the apothem times the perimeter divided by 2. And that's your formula for any regular polygon. And it's important that it's a regular polygon. But that's the formula for any regular polygon. So let's test this with a shape we already know. With a shape we already know the area to. Right? So if I do a square here, and I say this is 4 units, right? 4 units. Well, we can just look and go, this is 4, this is 4. We do base times height, 4 times 4, we get 16 is the area. But let's, I should put area equals. We know the area is 16 for a square like this, but let's prove it using this. Well, first we know that if we draw the apothem here, we know that the apothem is going to be 2 units because it's half of this side. So it's worth 2 units. And the perimeter is 4 plus 4 plus 4 plus 4, or 4 times 4, so we get 16 is the perimeter. And we can do this here. If we do 2 times 16 over 2, 2 times 16 is 32, over 2 is 16, and we get the area equals 16 units. So no matter which way we prove it, base times height, or apothem times perimeter over 2, we get 16 units, right? So now that we know this formula works, let's move on to something a bit more difficult. And you know what, I'm going to come up with my own examples here. So they might not work out perfectly, but that's fine. So let's say we have our shape here. We'll do our pentagon, if that were a regular pentagon. And I tell you that this is, 10 units, and the apothem is, what's the apothem? The apothem would be 6.88 units. Units on that. I know this is 6.88 units, but you can go and prove that the apothem is 6.88. But just trust me on this one. So if it's 6.88, and we go here and prove it with our apothem, 6.88 times the perimeter, 10 times 5, 50, over 2. If you do that, you get 172 units. if you plug that into a calculator, because I can't do that in my head. I have it written there on the book. But you get this is 72 units squared is our area of that shape. So it's that simple. But what if we don't have the apothem given to us, or what if we don't have a side length given to us, right? So let's say we just have, a triangle, a regular triangle here, like this, and I tell you the sides are worth 10 units, right? Now I ask you to solve for the area. Well, I mean, usually you would just do base times height, but here we don't have a height, so how do you solve for it? Well, first we can look, let's draw out our apothem here, right? And remember, the apothem is it's perpendicular and it's a bisector, so it cuts that into 2 equal halves. So let me draw this as 5 and 5 instead. And 5 on either side of our point here. And now what we can do is draw another line. If we draw the radius of this triangle out like that, now we have this right triangle, and we can solve for, and we can try to solve for this side over here, the apothem. We'll just call it x for now, and using that trigonometry. Well, first we have to solve for this angle here. And if you remember back in whatever chapter, I don't remember, but the internal angles are equal to 180 times the sides minus 2. So 180 times 3 minus 2 is 180 times 1 is 180. So we know all of these angles added together is 180. So if we divide that by 3 angles, because remember this is a regular triangle, so if we divide by 3, we get, 180 over 360. I know that I'm being stupid. We know each of these are 60 degrees, like that. So, and also remember that this is a bisector, an angle bisector, the radius. So we know that it's going to be half of 60, or 30 degrees, right? And 30 degrees like that. And now we can use the trigonometry we learned in the earlier chapter, chapter 6, I believe, to solve for this triangle. So let me pull this triangle out here. Right? And we have 5 units, x units, 90 and 30, right? And now this is super simple. So if we're dealing with, if this is theta, right? This would be the adjacent, this would be the opposite. Which one deals with adjacent and opposite? That's tangent. So if we take the tangent of 30 degrees equals our adjacent over opposite, 5 over x here. Now, if we bring x over, solve this, x times the tangent of 30 equals 5. And then we divide by tangent 30, we get x equals 5 over the tangent of 30. And we can plug that into the calculator, and you get 5 over tangent 30 is 8.66 about. So we know the apothem is 8.66. X equals 8.66, like that. And then from there, we can go back to our original triangle. If I write that out again, let me use blue. We go back to our original triangle, 10 units, and we now know this is 8.66 units, right? Then we do this. Okay, I don't know. We do 10 times 3 to get our perimeter. So we know the perimeter is 30. So we do 30 times 8.66 to give us 30 times 8.66 gives us 259.8, and then we divide that by 2, and you get 129.9 as the area. 129.9 is the area of the triangle. If I did that correctly. My note says something different, but I'm not sure. Yeah. But that's how you would do it. You just have to, use general intuition and solve for all the other values with what you already know. So let's go through and do a couple more examples. And, I know this is it looks pretty scary. And, you just got to work with it a little bit. Not get scared away, because that was a lot of math given one unit and told to find the area. It doesn't look possible at first, but, once you work with it a little bit, it'll be a lot easier. So here, if we have this pentagon, and I know that's not regular, but just pretend it is regular. And I tell you the apothem is 4 units. That's 4 units. It meets at a 90, like that. And I ask you to solve for the area. So go on, try that on your own for a second. Once you pause, figure it out. Okay, well, first, what we can do is try to solve for the angles, the interior angles of this shape, right? So what we would get is 180 times 5 minus 2, remember from chapter whatever, 180 times 5 minus 2 gives us 180 times 3. 180 times 3 is 540. So now we know that all of these angles added together is 540. So if we do 540 divided by the 5 angles we have, we get the angles are 108 apiece. So if I know that this here is, let me get a different color to work in. I know that this here is 108 degrees. And if I draw out the radius of this shape here, like this, I know it bisects that, so we want to take half of the 108, and we get 54 degrees here, degrees like that. And now with that, we can solve for this side right here. So again, if I pull this triangle out, just to make it a bit easier to look at, and we know this is 4 and 54, like that. And we want to solve for this adjacent here, and we have the opposite Well, that's going to be, again, dealing with the adjacent, opposite, and theta. That's the tangent. And with the tangent, you want to take the adjacent over the opposite. So if we call this side x, oh, that's the cat. I thought that was the camera falling. Okay, we would do x over 4 equals the tangent of 54, like that. And then you just solve this. You multiply by 4 here. You get 4 tan 54 equals x. And 4 times the tangent of 54, like that, is 5.5. 5.5, yeah. So we know x equals 5.5. So then we can put in here, back on our triangle, 5.5 is half of that side. So twice that is 11. So we know one side is 11. Then from there we take the perimeter. We do 11 times 5, right, is 55. So we do the apothem times the perimeter divided by 2. Right, apothem times perimeter divided by 2. 4 times 55 over 2. 4 times 55 is 220 over 2 is just 110. And you get the area is 110 units squared, because I know teachers get angry about that. 110 units squared. So a trick here, I guess, or not a trick, but the order in which you should solve is, you solve for a side, you solve for one of your sides. Well, actually, you solve for the angle. You solve for half the angle on one of your sides. Then you do trigonometry to solve for the missing side, whether it's the apothem or half. Then you find the perimeter times the apothem over 2. So your general plan should be like angle to trig to perimeter and then just solve for the area like that. So that should be your general plan when given one but not the other. I think we have a couple more examples, and then we go on to circles. And circles will be more fun. I mean, or circles will be easier. This stuff is fun, but circles are, definitely not a lot easier than this is. Just because this is taking a hard concept, trigonometry, and then making you understand it in depth to solve for something else, right? So you kind of have to, I don't want to say master, but you have to have a deep understanding of trigonometry and then apply it to do a third grade concept. There. Okay, if we take a hexagon, right? We take a hexagon, and I'll give you the apothem on this one. The apothem is 2 root 3, like that. So your apothem is 2 times square root of 3. And I want you to solve for the area of the shape of the hexagon, with it being a regular hexagon. So if you pause, try to figure that out. Okay. Now, right, if we follow our plan, we want to solve for the interior angles. So the interior angles would be 180 times 6 minus 2. 6 minus 2 is 4. 180 times 4 is 720, I think. 180 times 4. Yep, 720. So we know all of these angles added together is 720. So if we divide by 720 by 6 to solve for one individual angle, then we get 120. So I know one of these is 120 degrees. And if I take the radius of the shape, and that cuts this into two equal parts, so I can take half of this, 120 over 2 is 60. So I take 60 here, like that. And now I solve for this remaining side right here. Call it x. And now again, we want to use the tangent because we have the opposite and the adjacent. So we take the tangent of 60 is our theta is equal to the adjacent over the opposite. Or I apologize, it's the opposite over the adjacent. Have I been doing adjacent over opposite this whole time? And I apologize. Well, if you got the last two answers wrong, I'm sure they were correct because I was going too quickly. It's the opposite over the adjacent, not the adjacent over the opposite. That's why my book had different answers than me. So I apologize. I need to slow down, but that should be the opposite over the adjacent here. So the opposite is 2 times root 3. So we do 2 root 3 over x like that. And then we can solve this here by bringing x over. We do x times the tangent of 60. I think it's funny. I went on a rant earlier on how you need to be good at trigonometry for this, and then I messed up the trigonometry in the last two examples. But I apologize for that. Now we divide the tangent over. We get x equals 2 root 3 over tan 60. You plug that into your calculator. You do 2 square root 3 divided by tan 60. And you get 2. So this is x equals 2. So if x here equals 2, that means this entire side is worth 4. And then with that, you have to go there and then find your perimeter, right? If we follow that flow chart, if you will, we do the perimeter. 4 times 6 is 24, and then times our apothem, right? So we do 2 root 3 times 24 over 2, right? And then if you work that out, I don't know that off the top of my head, but if we do 2 root 3 times 24 over 2, and that is 41.56. That is 41.569, yeah. 569. And that is the area on this one. Right? 41.569. And that is the area of this shape here. I have one more, and then we'll go on to circles, and that'll take a little bit longer. I really thought this video would be, less than 30 minutes, but I'm guessing it'll be, 45. I haven't looked at the video time yet, but we have one more. If we have an octagon here, an octagon. That is a terrible octagon. It looks like a square. It looks like a circle. Let me 1, 2, 3, 4, 5, 6, 7, 8, like that. It's good enough. And I tell you that one side is 6 units, and I want you to solve for the area. So pause it, do that. Okay? So first we want to find all of the angles in the shape. So we do 180 times 6 minus 2, or 8 minus 2. Sorry, I got ahead of myself. 180, 8 minus 2 is 6. 180 times 6 is 1080. So that's what all of these angles add to, is 1080. So then we divide it by the 8 different angles in here to get one individual angle. So we divide it by 8 and we get 135. So this is 135 degrees. And then with that, we can draw our apothem and the radius here. So again, this angle is going to be half of the total. The total is 135, so half of 135 is 67.5. 67. Okay, 67.5, like that. And this is x, and we know that this bisects, so this is going to be half of the total, or 3, like that. And now you can solve for x. So if we pull the triangle out to make it easier to look at, and we say 3x 67.5, like that. It's a right triangle. And from there we do opposite over adjacent. Again, I apologize for that. Opposite over adjacent, we get x over 3. So we do the tangent of 67.5 equals x over 3. So from there we just bring the 3 over. We do 3 times the tangent of 67.5 equals x, like that. Plug that into the calculator. We do 3 tan 675, and we get 7.243. So we get x equals 7.243, like that. So then if we put that back up here into our original shape, 7.243, like that. And now we can solve for everything else by doing first we have to solve for the perimeter. 6 times 8 is 48 times 7.243. So 48 times 7.243 is 347.664. And then remember, we have to multiply it by 1/2 to get 173.832. So we know that our area equals 173.832, I believe. 832, yep. So that is the area of the shape. And again, this is just mind-boggling to me that you can solve for the entire area of a regular polygon with just one side length. But with that, now we'll get into partial area of a circle and area of a arc length. Give me just a second. And this one will be a bit more fun than that was. So first, what are we doing? So we're finding if we have a circle like this, we're trying to find, the length of this arc, the entire measure of that arc right there. Or we're trying to find the area of this section, this pizza slice, like that. So that's what we'll be doing. Now, how will we do this? Well, we're going to work with ratios, right? We're going to do the ratios between the entire circle and just that section we're working with. So first, let's start by finding just the arc length. So if we have, let me get a different color for the circle. If we have our circle here, and we'll just be real simple at the beginning, we'll do a 90-degree angle like that, and we'll say this is just 4 units there. And we're trying to find this arc length here, just call it S. So if we're trying to find that, we want to take, again, as I mentioned, ratio, the ratio between the entire circumference of the circle and just this section of the circle, right? Well, if we were to put, when you're solving for percents, you do part over whole equals percent over 100. That's what we're doing here. We're doing part over whole equals part over whole, right? So first we want to take this angle. That will be our first part. So again, this is just 90 over the total 360, or 1/2 pi over 2 pi over 360. And we set that equal to this distance here, this arc length, we called S, over the entire circumference. Remember, circumference is 2 pi r, so 2 pi, and then our radius is 4, like that. And then we just solve this for r, right? So first we can multiply by 2 pi fourths here to cancel it out. So we go 2 pi fourths times 90 over 360 equals S. Because I skipped a step where we bring that over, it's multiplied in front, and then we can just put it over a 1 and then multiply it in, right? And then with that, we can just plug that into the calculator, right? So, we go 2 pi times 4 times 90, all divided by 360, and that gives us 6.283 equals S. So 6.283 is this right here. And I mean, that should make sense, right? Because this is 1/4 of the entire circle, right? If you just rotate it around. And 90 over 360 also simplifies to 1 over 4. And if we take just the circumference, 2 pi r, 2 pi r, that gives us 25.13. And if we put 25.13, or if we put our 6.28 over 25.13, that also simplifies down. Here, if you can see that, 2.25 or 1/4, just like that. And same thing here, this simplifies down to 1/4. But when you're working with, different, like not 1/4, then it doesn't work quite as, it doesn't work like that. It's not as intuitive. You have to use this part whole, right? And that was the intuitive method of doing it. Now I'm just going to give you a formula. Now that we know how to do it intuitively, I'll give you a formula so you can just plug the numbers in and work with it. So if we say replace all these with variables, right? If we say this angle here is theta and this is the radius, that's just, we'll keep that s. We can say 2 pi r theta over 360, or if you're working in radian, 2 pi equals s. And that's the formula for doing all this. So 2 pi r, so your circumference times this angle, divided by 360 equals the arc length. Right, and now let's do the same thing for the area of the shaded region. So, we'll go back to this being 1/4, right? So we'll say this is 90, this is 4, and we'll call this shaded region. Let me get a different color. This shaded region here, A, like that. And we're trying to solve for A, right? Well, I mean, again, we know this is going to be 1/4. So what we can do is just solve for the area and multiply by 1/4. But what we can also do is the same part over whole, where we take the part of the circle or this part of the angle over the entire angle times the part of the area over the entire area. Right? So we take the part of our angle, 90, over our entire angle. Remember, a circle's 360 or 2 pi. And we set that equal to our part of the area, pi r squared, pi times 4 squared, over, or I apologize. I apologize for her. We take this area, we don't know what this area is, but we take A over then pi times the radius squared, 4 squared, like that. And now we can just simplify this. Let me lock that so she doesn't get back in here. Okay, we do pi times 4 squared. Pi times 16 is whatever. Oh, look at that, the door's locked.
Loser! I can still say it, loser!
So now we bring 16 pi over this way. I, again, apologize for her, but we bring 16 pi over. So 16 pi times 90 over 360 equals our area, right? So if we simplify this a bit, we bring 16 pi times 90 over 360 equals our area. And then just plug that into the calculator, right? So we do, when you plug that in, you're going to get, what? You get 16 pi times 90 over 360 is 12.566. So your area is 12.566. And again, that should make sense because if we take the entire area, 16 pi. Oh, shoot, sorry. 16 pi, that's about 50. And you take your 12 point, or you take this over the total area, and it simplifies down to 1/4 again. So it all makes sense, right? So let me give you a couple examples. Well, look at that. I just pulled the back of my marker off. But let me give you a couple examples here. If I can fix this marker, there we go. To work through. Like this. So if we go up here, okay. So this is our circle. I have 2 examples for you, and that works out to about 4 math problems. Well, it doesn't work out to about 4 math problems, it is 4 math problems. Okay, I have this. Here, this is 135 degrees. Like that. And this here is S. And this is 10 units. Like that. Our radius is 10. So if you want to pause, try to work this out yourself. Okay, so from here, we can take our part of our angle over our total angle. So 135 over 360 equals our part of the area. We'll do the area first. Part of our area over our total area. So A is our part of the area, and then our total area is pi times 10 squared. Pi r squared. When you simplify this down, we multiply our area over this way, and we do 135 times pi. Well, I don't need to put a multiplication there. 135 pi 10 squared over 360 equals the area, like that. And then just plug that into the calculator, right? 135 times pi, 135 pi times 100 divided by 360, right? And you get 117.809. 117.809 equals the area. And if you want this in terms of, if your teacher wants this in terms of pi, does this bring you joy, Hannah?
Yes. You bother me all day, loser.
Okay. If you want this in terms of pi, you can just divide out pi. So
Nerd, loser.
if we take this over pi, then you get 37.5 pi, and then 37.5, you do 37 times 2, 37 times 2, you get 72. So then you go, actually I don't know if you can still see this, then you get 72 pi over 2, and that would be your answer in terms of pi, if you need it in terms of pi. Right? So just divide by pi, and then if it's a fraction, put it over whatever makes it not a fraction, and then multiply by that. And that would be the area. Right? So I'll put that over there as our area. I'll put both answers, 117 and 72. And or 72 pi over 2 is more accurate. But instead of just rounding off, but it's all right. What is it? 117.809. Like that. And now we solve for the arc length. So first we do the part over whole equals part over whole. So part of our angle, 135 over 360 equals S over our entire circumference, 2 pi r, 2 pi 10, like that. And then we just bring this over, right? So we do 135 times 2 pi 10 over 360 equals S. And then from there, we just plug that into the calculator, right? So 135 times 2 pi 10 over 360 is 23.562. 23.562 equals S, like that. And if you want it in terms of pi, just divide out pi, put it over whatever makes it a whole number, and that would be 14 pi over 2, right? So you divide it by pi, you get 14.5 pi, and then you put it over 2, or you get 7.5 pi, you put it over 2, and then you get 14 pi over 2. And that's your answer for the S. S equals 23.562 or 14 pi over 2. Like that. And that's your answer for problem number 1. Problem number 2. I bet you this video's at an hour right now. Even I thought it was going to be like 30 minutes. Let's see. What are we at? We're at 57:38. Yep. Okay. We have one more circle. I'll try to go through this one quickly. See if I can keep it under an hour. No, I can't. It's at 57. There's no way this will take less than 4. Okay. If I have this, we have this arc length is 18, and this is, the radius is 10, and I want you to solve for theta. Well, if we go back and remember our formula for earlier, right, where it was 2 pi r theta over 360 equals S, right? So if we just plug in 18 for S, and then we isolate theta, we can just, then we can solve for theta, or for our angle, right? So first we bring the 18 over, right? So we just divide by 18, or just, what? I apologize. I don't know what I'm talking about here. Right, but we divide by the theta over 1, so we can bring it over here. We do 2 pi r over 360 equals 18 over theta, like that. Just multiply by the reciprocal. And then from that right, I did that. No, I did not do that right. I don't know what I'm talking about. We're supposed to multiply by 360 over 2 pi r on both sides. See, whenever these hit about an hour, I stop thinking properly. So if we have this here at 2 pi r theta over 360 equals 18. So we multiply by the reciprocal, right? We flip it, so that would be 360 over 2 pi r, but we leave theta behind. So we get theta equals 18 times 360 over 2 pi r, like that. And then from there, we just solve for whatever 360 times 18 over 2 pi r is. Plug that in. We do 360 times 18 over 2 pi. Our radius is 10. And we get 103.132. 103.132. Right? Like that. And that is your answer. So theta equals about 103 degrees. And that is chapter 11. Next, chapter 12, last chapter, almost done. Hopefully these are out by August 1st. I mean, it is, July 30th when I'm filming this, 2026. So if I just film tomorrow and I get both of these posted, it should be out. Next is, we already did scaling of 2-dimensional shapes. Next is scaling of 3-dimensional shapes. And this this is simply one page of information. It won't take 10 minutes. So I may just do it today, honestly. But go on to chapter 12.